Okay, so now it's all right.
Yeah, good.
Okay,
yeah, thank you.
So this is Rong Yu from Renmin University of China, and first thanks organizers for inviting me to give this talk here to this symposium. And today I would like to talk on the orbital selectivity, and we actually started from the iron trichononite system to the iron nuclide system recently. Okay, so these are my collaborators. Mr. Lin Hui Hang is a graduate student in my group. And for the theory part, we also collaborated with Dr. Jianxin Zhu at Los Alamos National Lab and Professor Qimiao Xi's group at Rice University. And we also collaborated with the Professor Ming Yi's group at Rice University on the RPAS experiment. So here's a outline. I will give a very brief introduction to the electron correlation effects in the iron-based superconductors, with focusing on the orbital selectivity, which is actually a multi-orbital correlation effects for the multi-orbital systems. And I will mainly talk on the orbital selectivity in both the iron triquartite system, in this doped iron selenide system, and also on this iron nictide system. It's a lithium-111. And in particular, we find that the orbital selectivity will give the very strong renormalization of the electronic structure and the reduction of the Fermi surface in this compound. And at the end of this talk, a summary will be given. Okay, so shortly after the discovery of the high temperature superconductivity in the iron nictides, it has been recognized that this system consists of considerable strong electron correlations, as one can show here in this optical conductivity data. The Druid weight is considerably suppressed from the band theory values. So this will suggest, this actually suggests that the parent iron nictide system is actually a bad metal. And another evidence of very strong electron correlations in these iron-based superconductors, it can be actually seen from this global phase diagram of this system. So the superconductivity actually appear close to a antiferromagnetic ground state, which actually suggests the antiferromagnetic spin exchange interactions is very important for the superconductivity in these systems. Okay, but besides the antiferromagnetic spin exchange couplings, we have to also recognize that the iron-based superconductors are multi-orbital systems because the Fermi surface consists of multiple sheets with both hole pockets at the center of the brane zone and also these electron pockets at the boundary of the brane zone. And also the multiple orbitals, the 3D orbitals of irons are not all degenerate. It's actually a partially degenerate with a doubly degenerate XZ and YZ orbitals, and all the other 3D orbitals are actually non-degenerate. So this is a very complicated multi-orbital model. So if we started from a theory, we'll see that we can consider actually a multi-orbital Hubbard model for the iron-based superconductors. It consists of the non-degenerate orbitals with a finite interorbital kinetic couplings. And also, if you look at the interaction part, it consists of competing interactions with the intraorbital Coulomb repulsion and also the interorbital Coulomb repulsion, and also very importantly with this Honsrud coupling interaction. And this will give a very rich physics for this model. And for example, depending on the strength of this Home-through coupling and the strength of the level splitting, the delta, the system can be either stabilized in a high spin state or in a low spin state. So it is actually natural to expect that the correlation, the strength of the electron correlations are actually very strongly orbital dependent, means that they are not the same for all the 5 iron 3D orbitals. And then we actually need to identify which orbitals are the most important for the magnetic order or the antiferromagnetic order, and also for the superconductivity in these systems. So we actually first focus on the normal state properties. In general, if we consider a multi-orbital system, say let's consider 2 orbital system, if there is a very strong orbital dependent electron correlation effects in these systems, we call this system has a very strong orbital selectivity. And in the extreme case, one orbital can be in a metallic phase with a itinerant electrons in this orbital, but the other orbital can be inside a most insulating phase, where the only active degree of freedom are the spins, but not the charge degree of freedom. Okay, so we call this system is in a orbital selective mode phase. Okay, but in the experiment, usually the different there are hybridizations between the different orbitals, and then the orbital selectivity can be measured, or usually measured by this effective mass renormalization factor, the m star over mb. If we see a very strong orbital dependent mass renormalization factor, usually this corresponds to a strong orbital selectivity, which is a precursor to the orbital selective mode phase. So in the iron-based superconductors, this orbital selectivity has been extensively studied, both theoretically and experimentally. And especially for the experiment, it has been recognized that the orbital selective mode behavior is kind of a universal behavior for all the iron trigonionized system, both for the doped iron selenide system, or the single layer iron selenide system, or this potassium iron selenide system. And in all these systems, when increasing the temperature, the system seems to goes from a bad metal phase to a orbital selective mode phase, as shown in this very nice paper by Professor Ming several years ago. And how to study this orbital selective mode physics theoretically. And here we propose to solve for the 5 orbital Hubbard model for the iron-based superconductors by using the so-called U1 slave spin formulation. So here is the model. It consists of a type binding part and a interaction part with the U prime, and the J Holmes terms. And in the U1 slave spin theory, we introduce a quantum spin 1/2 operator to carry the charge degree of freedom, and also a fermionic spin-out operator to carry the spin degree of freedom. And to rewrite the electron creation operator in terms of this slave spin and this fermionic spin-out operators. And we also introduce a constraint to limit the Hilbert space in the physical sector. And to get the saddle point solution, we rewrite this electron creation operators in terms of the Z addressed slave spin operator and a fermionic spin-out operator. So here the address operator is proportional to this slave spin operator previously introduced. And then at the saddle point level, we obtain 2 Hamiltonians, one for the spin-out sector and the other is for the slave spin sector. And we solve these two Hamiltonians self-consistently. And we can get basically three different solutions. So if the quantiparticle spectral weight, the Z, are all non-zero for all the orbitals, the system is in a metallic phase. And if the quantiparticle spectral weight Z is zero for all the orbitals, this is a molten insulator. And interestingly, we also find there is a third solution, which corresponds to this orbital selective mode phase. So in this phase, for some orbitals, the quantiparticle spectral weight becomes a zero, but for other orbitals, it becomes a non-zero. Okay, so we first apply this U1 slave spin method to study the electron correlation effects in this potassium iron selenide system. And here is the ground state phase diagram. And we can identify the three phases: a metallic phase, a molten insulator phase, and in between there is an orbital selective mode phase. So inside this orbital selective mode phase, we see that the quantiparticle spectral weight in the XY orbital becomes zero. Means that this orbital is inside a molten insulating phase, but all the other 3D orbitals of irons are still itinerant with a finite quantiparticle spectral weight. And we also find that for this potassium iron selenide system, the orbital selective mode phase can be induced by increasing the temperature, and from a bad metal phase to this orbital selective mode phase. Okay, and this is also seen by the RPAS experiment. Okay, so more recently, we look for a orbital selective mode phase which can be stabilized as a ground state in the iron trigonalite system. So we collaborated with Professor Ming Yi's group on this compound, this iron selenide system doped with tellurium. So we can actually find a orbital selective mode transition from a bad metal phase to a orbital selective mode phase by doping from the iron selenide side to the iron telluride side. And at the same time, we find that across this orbital selective mode transition, there is a reconstruction of the Fermi surface. So for example, for x equals 0.5, we see there is this faint, but still we can see this dxy like whole, very big whole pocket centered at the gamma point. But once we are inside this orbital selective mode phase, when x equals to 0.1, we see that the Fermi surface consists of ellipse centered at x point. So for the details of the experiment, I'll refer to this talk by Dr. Huang in this same section. And also I refer to our recent paper post archive. Okay. And why there is this reconstruction of the Fermi surface in this iron trigonalite system? And we can take a further look about the band structure in this system. So for x equals 0.5 in the bad metal phase, we see the dxy orbital is strongly renormalized. And because the dz square and the dxy are hybridized along this gamma to x direction, which corresponds from the zone center to here. And then we'll see that once the dxy orbital becomes strongly renormalized, this will actually push the dz square to be closer to the Fermi level. And for x equals 0.1, when the system becomes inside this orbital selective mode phase, the dxy orbital becomes totally incoherent. And then this will lead the dz square band to cross the Fermi level, which give rise to the reconstruction of the Fermi surface. Okay, so this is what happens in the iron trigonalite system. So now I will transfer to the orbital selectivity in the iron pnictide system. So we are actually looking for a system which also exhibit a strong orbital selectivity. And also we asked whether we can find a signature of the electronic reconstruction caused by the strong orbital selectivity in any iron pnictide system. And we actually find a very interesting experimental result given by Miao et al. In this paper. And they actually find a very strong temperature-dependent spectral weight evolution. So when increasing the temperature, they see the spectral weight in the XY orbital becomes reduced. However, the spectral weights for the XZ and YZ orbital almost keep a constant in this lithium-111 compound. So we studied the orbital selectivity in this lithium-111 compound. And another point which motivates us to study this system is the reduction of the Fermi surface in the lithium-111. So according to the DFT calculation, there are 3 hole pockets centered at a gamma point. However, in the experiment, they actually find that the lower the band, which is the alpha prime band, which account for the innermost hole pocket, is actually below the Fermi level. And even in a study by Professor Rosa Valentis' group, even they perform this DFT plus DMFT calculation, it doesn't seem to change too much from this DFT results. However, if they apply this non-local electron correlation effect using this TPSC method, and then they see the reduction of all the electron and hole pockets, and also the inner pockets becomes reduced. So this raises a very interesting question that whether one really needs this non-local electron correlation effects to see this reduction of the Fermi surface. Okay. So here are our results on the orbital selectivity in the lithium-111 system. So here is the ground state phase diagram. And this is very similar to the phase diagram in the iron tricoordinate system. We actually identify a very broad regime where the ground state can stabilize a orbital selective mode phase, even for this lithium-111 compound. And the nature is also similar. So inside this orbital selective mode phase, we see the dxy orbital has a 0 quasi-particle spectral weight, which means that this is already most localized, while the other orbitals are still itinerant. Why we see such a strong orbital selectivity in this lithium-111? However, we did not see the similar behavior in, say, this 1111 compound. We actually compare the density of states projected to this dxy orbital and versus the total density of states in these 2 systems. And actually, we indeed find that the density of states projected to the dxy orbital in the lithium-111 is getting narrower, much narrower than the 1111 compound. And this is actually because in the lithium-111 compound, the iron arsenic bond angle is much smaller. And because of this smaller bond angle, this will reduce the interorbital hopping associated with the dxy orbital and give a narrower bandwidth. And this will account for the calculated the strong orbital selectivity in this lithium-111 compound. Okay. So given the proximity to this orbital selective mode phase at the ground state, we expect to see a transition from a band metal phase to to a orbital selective mode phase by increasing the temperature. And this is indeed shown as in the calculated result. And we can identify a orbital selective mode transition at about 230 Kelvin, where the dxy orbital becomes fully localized, while the dxz and yz orbitals are still almost itinerant. The quasi-particle spectral waves of the dxz and dyz orbital almost keep a constant. So as observed in the RPS experiment. And now we turn to the renormalization of the band structure. So we find that the strong orbital selectivity not only lead to the strong renormalization of the bandwidth, but also lead to the renormalization of the energy levels, as shown in this plot. So for both the dxz orbital and the dxy orbital, we see a strong renormalization of the energy levels. And I show here that this strong renormalization of the energy level will cause the reconstruction of the Fermi surface. So close to the gamma point, the dispersion of the whole bands can be approximately written in this way. So it includes a non-interacting Fourier component of the hopping parameters, which is renormalized by the quasi-particle spectral weight at orbital alpha, and then plus a level energy. So it's which is also renormalized in this way. However, if there is a strong orbital selectivity, the renormalization factor Z prime is going to be different from the Z, from the quasi-particle spectral weight. It's a complex function of the quasi-particle spectral weights of all the orbitals, actually. So means these two are different, okay? And then this will lead to the reconstruction of the Fermi surface in the presence of finite electron correlations. So we first determine the Kf at u equal to 0. So then this is determined by this equation. So the C alpha plus this epsilon alpha equal to 0. And in the presence of electron correlation with finite u, the Kf is actually determined by requiring the dispersion E of k equal to 0. So that means that the entire thing becomes 0. And we see that if there is a strong orbital selectivity, the Z prime is not equal to Z, and then this will lead to the Kf not equal to the Kf 0. So this will immediately give us the reconstruction of the Fermi surface. And then this is indeed shown in our calculation. And especially we find two features. One is all the pockets, including both the hole pockets and the electron pocket, just shrinks. And then most interestingly is for the inner pocket, the innermost hole pockets, we find that it's fully eliminated if we apply a finite u, where there is a pretty strong orbital selectivity. Okay. And to see this, a reconstruction of the Fermi surface is indeed associated with strong orbital selectivity. We take a closer look at the band structure at u equal to 0 limit and at finite u. And we focus on the band, the bottom of the gamma band, which has mainly a XY orbital character. And we find that it is renormalized by a factor of about 5. However, for the delta band bottom, which mainly has the dxz and yz orbital character, it only renormalized by a factor about 2. So this indeed shows a very strong orbital selectivity in this system. Okay, and we also find that there's also this strong renormalization of the dxy, this beta band close to the gamma point, and also this will push the dz square band to be closer to the Fermi level. And this is very similar to the case of the iron trigononite system. Okay, so then here is a summary of my talk. We studied the orbital selectivity in multi-orbital models for both the iron trigononite and iron nictite system. And we indeed find some universal properties in these two systems. And in particular, for the lithium-111 compound, we find the reduction of the Fermi pockets, which is associated by the strong orbital selectivity. And this can be understood by including the local correlations alone. And I would also say some words on the superconductivity. Basically, the main driving force for the superconductivity is the spin exchange, antiferromagnetic spin exchange couplings. However, in the case of strong orbital selectivity, the superconductivity both is a pairing structure and the gap structure can be strongly influenced by the orbital selectivity, which lead to this orbital selective superconducting pairing. Okay. And thank you very much for your attention.
Yeah, any questions for Ron?
Yeah, I have a question.
Okay.
So can you actually, both for Ming Yi and for Ron Yu, what is the position of the XY level relative to the XZYZ in the chalcogenides in your calculations? Because my understanding is that many experimentalists claim that the XY orbital is below the Fermi level, not above.
Right. That's right. So you can see actually from here. Yes. So actually for this model for the FET SE, actually this is the blue portion is actually the DXY.
Yeah. So
and then it actually cross because there is a finite orbital spin orbital coupling. So it's not this one, but actually goes this way. In the model, it is still slightly above the Fermi level, but I think this is I don't know. This is probably just a detail of this model. But it's pretty close. Yeah.
But I just want to know who to believe, because I agree this is a detail, but now I mean at this level of calculation is just a question of detail. So are they experimentally sure that the DXY, that this is not correct and the DXY lies below? So the DXY pocket is smaller than the XZYZ pocket.
Sure. I think for this experimental part, since I did not prepare a experimental slide, so maybe you can see the result in the next talk. I think it's pretty close to the Fermi level. That's a conclusion, which can result to this whole pocket.
So this doesn't agree with other experimental groups. I mean, I don't have a horse in the race. I mean, I haven't worked on that for 12 years. So I just want to know what is true.
I think the theorists probably should let experimentalists address this.
Yeah.
I guess, so there is a hybridization which is seen between the XY whole band and the XYZ whole band near the gamma point, at least for the optimal substitution level, which I guess you can probably see from the cut in the next talk.
But for the iron telluride, do we know the answer?
I don't have the data in front of me, but I guess maybe after the next talk, when we see the slide, we can come back to this point.
Because again, if there's an orbital selectivity, there should be no hybridization. If you're really deep in the mod phase.
Right. So as we see tuning towards iron tellurium, we see the hybridization. We don't see the hybridization as much. I mean, there will come a slide. Sorry, my is giving a talk. He had the slides ready, but there will be a slide on the cut as a function of the substitution level.
Okay. So let me ask you, Ron. I mean, are you for the lithium iron arsenic? Are you also suggesting which orbital is responsible, DYZ or DXZ?
Responsible for what?
For superconductivity.
Oh, that's a good point. Okay, that's very good point. Very good question. So for this one, I think at least there is a reconstructed Fermi surface. Means that the innermost one is actually does not exist, right? So actually means that this I think will challenge this Fermi surface nesting picture. So I do think that the dxy orbital will contribute to this superconductivity.
Oh, to the pairing?
To the pairing, yeah. But we haven't did this calculation. We're going to do this. Yeah.
And here another question from an experimental perspective and a theoretical perspective. Once you are in the orbital selective mode phase, are you saying that the experimental Fermi surface violates the Latinger theorem?
No, at least theoretically it's not.
No, sorry. Once you're in the orbital selective mode phase, you should violate the Latinger theorem.
I don't think the Latinger theorem is violated.
Well, the XY is kicked out, so in that sense, I guess it is, right?
Yeah, it is. I mean,
it
you
is,
have to violate the Latinger theorem.
In practice, you have to fight the magnetic order, but
okay, but yeah, okay. It actually depends on how you count the number of the electrons. Yeah, sure. In that way, I think you're right. It is violated in that way. Yes. Yeah.
Okay.
Experimentally, Mingyi, did you really check the Latinger volume? In the lithium arsenide, I'm 100% sure. We spent a year doing a very careful job, understanding the photon energy dependence, everything. Latinger theorem works beautifully. Even though there is KZ dispersion and all sorts of complications, I can assure you it works.
But nobody would disagree with that, Gabby. For lithium,
well, no, if you have an orbital selective mode transition, you should not agree because you should
no. At the zero temperature, lithium ion arsenic is in the itinerant state.
Okay.
Yeah, let's have this discussion a bit later, right? Let's have the last talk. Yeah, let's thank Ron again. Yeah.
Thank you.
Thank you, Ron. Yeah, for a nice talk. Yeah, so Jianwei, it's your turn. Yeah, just go ahead. So we're running quite late. Yeah.
Okay. I'm going to share my screen.
Yeah, you can just carry on.
Okay. Great. I'd like to thank the organizer for inviting me to present in this great symposium. I'm Jianwei Huang. I'm a postdoc in Mingyi's group. So the title of my talk today is this orbital selective correlations in this iron tellurium selenium series. I will call it FTS for short. So first of all, I'd like to acknowledge our collaborators, which our APEX experiments was assisted by Donghui and Makoto, Jonathan and Sangkun. Our theoretical calculation was done by Rong, Qimiao, and Jianxin. The whole resistivity measurement was done by Junhao's group, and our beautiful samples was provided by Zijun, Genda, and Peng Chen's group. So first, I will quickly recall the basic property of the iron-based superconductors. So here I'm showing these polycenter tetrahedral crystal structure of this archetype iron-based superconductors, berry iron arsenide. It is generally agreed that the iron nictrogen layers is critical as it is the building blocks of all the iron-based superconductors, and is where the low energy electronic structures originate from. DFT calculations have shown that the iron 3D orbitals occupy the lower binding energy, which are around Fermi level, while these nitrogen p orbitals occupy the higher binding energy. Furthermore, the nitrogen crystals split these 3D orbitals, which make the 3 T2G orbitals lifted slightly above these EG orbitals. eventually, what we will see is the Fermi, the electronic structures around Fermi level is mainly consist of XZ, YZ, and XY orbitals, which will form this whole pocket around the gamma and the electron pockets around the Brilliant Zoom corner. So it is generally believed that the iron-based superconductors possess this moderate electronic correlation strength. It is not as strong as that in the cuprates, but it is definitely non-negligible as in this simple matter state. So the moderate electron correlations of the iron-based superconductors are manifested by its bad matter behaviors. For example, they have a larger resistivity compared with the simple matter, and we observe these suppressed peaks in the optical conductivity spectrum, and we see these large ordered moment or the large fluctuation moment in the iron-based superconductors. There are two things that we know about these correlations for the iron-based superconductors. First is the iron chalcogenide basically possess larger electron correlation effects than the iron nictides. Second is the electron correlations in the iron-based superconductors exhibit this orbital selective behavior, which the XY orbital, the band of the XY orbital always exhibit a larger mass enhancement than other orbitals. Later, it was found that actually the electron correlations in the iron-based superconductors can be related to these iron nictogen bound lengths. It can be understood that in a way that the iron hoppings through these nictogen atoms was reduced by increasing this iron nictogen bound length. So especially in this iron chalcogenide, which possess larger electron iron nictogen bound lengths, we find that in this iron tellurium compound, the DXY orbitals experience a very larger mass enhancement. With which we can find that its quasi-particle coherence factor reduce close to zero, while the orbitals still possess considerable spectral weight. It is these strongly orbital selective correlations really sits very close to this orbital selective model phase, which the DXY orbital totally gone. So actually, the orbital selective model phase was theoretically proposed to exist in these iron-based superconductors. Orbital selective phase generally describes like in a multi-orbital system, particular orbitals turns are localized while the others still remain itinerant. In the case of iron-based superconductors, it is the DXY orbital localized, but all the other orbitals remain itinerant. Three conditions are needed to realize this OSMP state, which first we need the crystal field to split the XY from the XZ or YZ orbitals. Then the XY bandwidth need to be smaller than XZ and YZ without considering the electron-electron interaction. Third, we need a Hahn coupling to suppress the interorbital interactions so that the different orbitals cannot talk to each other. With all this, we should ask these questions. Can we really realize an orbital selective ground state in the iron-based superconductors? So in the following talk, I will persuade you that we really find that this iron tellurium is in proximity to the orbital selective mode ground state by first present you this universal OSMP crossover induced by temperature. Then we show that there are four observations that really tell us the FT is in a proximity to the OSMP ground state. First is this selective divergence of this band effective mass. Then we find this redistribution of the Fermi surface spectral weight. The third thing is that we find that the dxy in cohesion temperature decrease toward this iron tellurium end. The third is to find our RPS observations consistent with this whole resistivity measurement. First of all, this temperature-induced optical selective has already been found previously. This is a gamma M cut. Sorry, this is a gamma M cut for this FTS with selenium content equals to 0.44. We find that the low energy band consists of these XZ, YZ, and XY orbitals at the low temperature. With the increase in temperature about 120 Kelvin, we find the spectral weight of the dxy orbiter near Fermi level is strongly suppressed. And concomitantly, we find that the gap at the endpoint, which is caused by the strong hybridization of these XY orbitals with the XZ orbiters, also disappear. To quantitatively analysis these, we plot the spectral weight of the XZ and YZ orbiters by fitting the EDCs across these at this yellow bar position, and we find indeed the XY spectrum weight decreased to 0 at around 110 Kelvin, but while the YV orbiter still remains considerable spectral weight. Later on, our experiment also will captured by the theoretical calculations. And later on, the temperature-induced orbital selective Mott crossover was found to be universal in these iron chalcogenide families. No matter, despite they have different crystal structures and different Fermi surface topologies, you always find the dxy spectral weight drops to 0 with increased temperature, with YZ still possess considerable spectral weight. And besides RPS, there are also other props that report this orbital select Mott crossover induced by temperature, like this combination of the resistivity, heat capacity, thermal expansion, and the susceptibility. Also, this orbital spectroscopy measurement on these potassium iron selenium. So now I'm going to show you how we've tuned this tune towards OSMP ground state by reducing this selenium. First, we have shown that we have previously shown that in this iron tellurium selenium, the optimum compound, we can induce this OSMP state by increasing temperature. Then how do we, what if we tune across this x-axis? In this previous diagram, we find that we substitute a selenium with tellurium, the ion bond will increase. So the XY orbital tends to go will undergo a much larger mass enhancement. So we plot we did this experiment. We plot the gamma M cut of different iron tellurium selenium compound, which shown this shown in this phase diagram here. To better all these cuts was taken at low temperature around 10 Kelvin. To better show the band dispersion, we take a second derivative, and we fit this band with a parabolic curve to extract the effective mass. First, let's take a look at the DYD orbitals. We find that the effective mass of the DYD orbitals does not change much. But for the XY orbitals, we find a much stronger effective mass towards iron tellurium end. We plot our fitting results here, and indeed we find a divergent behavior of the effective mass enhancement towards this iron tellurium end. And then we plot this quasi-particle cohesion factor extracts from this effective mass enhancement. We find that it decreases, and a linear extrapolation tells us this z extrapolates to around 0 at this iron tellurium end. Second, we observe this strong Fermi surface spectral weight redistribution. So the right figure shows and the optimal doped compound, which shows the hole pocket around the gamma and electron pocket around M. This is normal. But for the iron tellurium, we find that there is spectral weight appears around this X point of the Brillouin zone. So where does the spectral weight of the X point evolves? We plot this systematic evolution of the Fermi surface. First thing we see is these the electron pockets expand from the iron selenium to iron tellurium. Then we find that the phalant dxy orbital, the spectral weight gradually evolves to this spectral weight around this X point. To quantitatively extract this spectral weight evolution, we integrate this spectral weight around this inside this rectangular, and we plot the spectral weight evolution here. The evolution really reminiscent of the effective mass evolution we have shown before. So this really shows us that this iron tellurium is really in proximity of this OSMP state. So then here is the question. So where is this spectral weight come from? So our theory collaborators have done these calculations based on this U1 slave spin theory on this multi-orbital Hubble model. So for this x equals to 0.5 FTS, this state is in this this sample is in this strong correlated matter state. Well, we find that the square orbital which cross this Fermi level around this X point is gapped by the hybridization with XY orbital. So in this case, it shows this normal Fermi surface with the hole pocket around gamma and electron pocket around M. But when the sample went into this OSMP state, the DXY orbital becomes totally localized. Then the square orbital cross the Fermi level, and the spectral weight around X point appears. This their calculation shows greatly consistent with our experimental observations, and with all this, let's take back to look what we have learned. First, this is the first diagram with this TC, TS, TN. At the iron selenium end, we find that it is a strong correlated matter. With increasing temperature, the DXY orbital will become incoherent. For this iron tellurium compound, it is in proximity to this OSMP state. It's a ground state. So suppose we go from the iron selenium to iron tellurium, we will expect a decrease of the DXY orbital cohesion temperature. So let's check whether this is the case. We plot what we have to do before. We plot the spectral weight of different orbitals from two different samples of the FTS, one with the higher selenium content, one with the lower. We find that the FTS with a higher selenium content shows a higher DXY and cohesion temperature, but for the compound with a lower selenium content shows a lower DXY and cohesion temperature. So this really agrees with the iron tellurium as a OSMP ground state. Well, and with this, we come to our brief conclusion with a summary, which first we observe this dxy orbiter become totally incoherent with increase in temperature. Second, we observe this the effective mass enhancement, that it diverges towards this iron tellurium end. Then we find that these are a redistribution of the Fermi surface spectral weight, which is very likely induced by this incoherence of this dxy orbiter. Third, we find that the dxy incoherence temperature decreased towards this iron tellurium end. So we draw this conclusion that our iron tellurium is in proximity to the OSMP ground state. And this is not the end. We have done this Hall resistivity measurement on this FTS series. And we find that this common feature is that the Hall resistivity as a function of temperature shows a hump and a side change. So there are two interpretations of this behavior. One is this hump and the side change is caused by the incoherence of these dxy portions of the electron pockets around the endpoint. The second interpretation is that it's the suppression of these pi fluctuations with this dxy incoherence. Both interpretations also tells that us that these characteristics temperature really marks where the dxy orbital become incoherence. We plot this correct temperature here. It's really the trend really matches our RPS evolutions well. And so based on all the observations, we draw the conclusions that these iron tellurium and compound is indeed in proximity to this OSMP ground state. So that's all. Thank you. I didn't put the band structure evolutions here, but I have it in the supplement if you want to look. Oh.
Okay. Yeah. Thank you.
I have the same question I asked before. What's the value of the crystal field splitting? That's a number. You know the number. And why do the people who do iron selenide claim that the XY orbital is below the XZYZ?
I think we agree with that, Gabby. So on iron selenide side, is indeed below the XZYZ. I don't think there's inconsistency on that side.
Well, but in all the calculations that they show me with this model, that's not happening.
So, yeah, here is the hybridization slide, right? So I guess the rightmost doping substitution level, you can see the hybridization between the XY whole band and the XZ.
So let's see, do you have a pure iron selenide in this? No.
I guess we don't, yeah.
Because it would be really wonderful if the experimental groups can agree on the facts. I tried to lay out the questions for the theories, and you should measure the volume of your Fermi surface. It's really easy. I convinced Humiao to do the integrals. You have a great student, he can do the integrals, and then you get a number.
But Gabby, I mean, they have done a polarization study for you, and they have identified at low energies near the Fermi energy where the XY states are and where the XZYZ states
I just
are.
wanted
So
drawing on the Fermi surface. The polarization has nothing to do with it. The polarization just tells you what.
No, there is a Fermi surface, right? The Fermi surface will show the contrast between 50-50 and FETEN is something that you see by the naked eyes. And there's a big pocket near X that's developing near FETE that's not there in 50-50, right?
Beautiful. So I like that because that's the cleanest example that there is an orbital selective mode transition. There is a
and I thought Gabby, you would like it in the following sense. You know,
is getting contradictory information from different experimental groups. That's why.
Well, the other experimenters are not speaking here, so maybe we should bring in a discussion in a different forum. But what I want to draw your attention to is that there's some beautiful evolution of the Fermi surface that in other materials, such as heavy fermions, it's very hard to use APAS to see, right? Here, you are visualizing the K-space directly, and there's something to be understood. Why there's a big region near X that's developing as you go from 50-50 to FETE. And I was very surprised for a long time.
My request is to add to this the iron selenides, so we have a complete set.
No, it would be nice, but already you have this contrast. They worked very hard for this.
And then I would like to have the not just the drawings, but then the integral, which is just a number, just to see what it's just a test on the experiment, just to see by how much it jumps. I just cannot do the integrals in my head. That's just some suggestions how to analyze the data.
I think a Luttinger volume would be extremely beautiful to analyze, but having thought a lot about Luttinger volume in the context of heavy fermions, here the background conduction electron states, they are a curse and they are an advantage. The curse is that you have dxz, dyz, dz square, and you have 4 d band orbitals, which are all from the perspective of orbital selective mode, acting as a background conduction electron states. The advantage is that something like a z square you can really track. So there's some well-defined the analog of what we call the SPD states of the heavy fermions that you can zoom in and these they spend a lot of time looking at it, and turns out that's extremely illuminating. In other words, you can look for hybridization and its breakdown near gamma, and experimentally it's very hard, and there's some feature that's there. It turns out the breakdown of hybridization is just in your eyes if you look at the right place, which is look at near X, where the dz square crashes down or not, depending on whether the hybridization is there or not. So there's something experimentally extremely beautiful there from the perspective of Luttinger volume, without looking at the much harder issue of counting Luttinger volume, which is very nice to do, but much harder.
Yeah,
okay.
I'm just making some obvious suggestions that it's really important. In gamma, we understand everything, so we should know the order of the levels. I would like to know how large is the crystal field. I mean, just some basic things that can easily be done.
And any other questions?
Gabby, I think there is a practical concern from photoemission experiment point of view that it's far from obvious you can get an accurate Luttinger volume counting. On the one hand, there are so many bands in pnictides, it's very hard to precisely determine KF. And on the other hand, there is a 3-dimensional Fermi surface, so you cannot just count the area on the map. You actually have to.
I know on lithium iron arsenide we did that job. I mean, so I don't see any reason why it cannot be done. Here
it can be done. It's just the error bar has to be convincing.
Sure, and yes, that's true.
Yeah, I guess in this case the pockets are smaller than the lithium iron arsenide. The XY pocket is quite large. I guess I mean you're not gonna you're not gonna take all this things that were the experimental details that may add up, but we'll try. Yeah.
And I would like to also your data on the iron selenide side. Then we have a comprehensive picture. I think it would be nice if the community can converge on what's known. I think this is beautiful work. I think it's really important. It's very nice. Just it becomes even nicer when you reach consensus with the other groups. Mm-hmm. And I think it's
sorry, I was going to just add on point, if I may, just on this point. FESE has a life of its own, Gabby, with nematicity and all that.
You measure at 100 Kelvin. There's no nematicity at 100 Kelvin.
We have that data. I mean, I don't think in terms of data, we have any disagreement on iron selenium. We have done that work last year regarding to look through the Fermi surface through the phase transitions.
Yeah,
And
so
that,
like
yeah.
100 Kelvin, how does the XY orbital? Because you see the theories feed on that. There's a paper 1 week ago of Luca De Medici, which in fact I agree with, which is very nice, but it's all based on the fact that the crystal field levels got inverted in the iron selenide. And I would like to know if it's true. I mean, what I try to say in my talk is that if you look at it from the perspective of resources and the time that the community is spending on this and some rational way, there are some obvious questions that could be clarified.
I see.
think
So
we should
mostly
list
concerned
that
about
question.
iron. Okay, yeah, okay.
I think
On
we
iron
should list
selenium
the
side,
crystal level scheme as part of the discussion questions. It's interesting and important.
Okay, Gabby has
and how to make progress.
Whether to know the Lothinger liquid. I mean, yeah, well, that's actually an interesting point. Yeah. Any other questions? Okay, so if not, I mean, it's getting quite late. Yeah, let's thank all the speakers, and then
okay,
we'll
very
see.
nice. Good to see you guys.
See you, Gabby. Yeah. So
Bye.
let's
thanks for staying all the way.
Yeah, continue this tomorrow. Yeah, thank you.